So good afternoon, all of you. Very happy to welcome you all for this afternoon session. Myself, Anju, Assistant Professor, Department of Information Technology. Today we have an excellent session on how to outsmart crypto thieves with blockchain-based security. We have an eminent speaker for this session, Professor Shekhar Verma, IIT Allahabad. Shekhar Verma received the PhD degree in Computer Networks from the Indian Institute of Technology, Varanasi in 1993. He is currently working as a professor with the Indian Institute of Information Technology, Allahabad. His research interests include machine learning, computer networks, wireless sensor network, information, and network security. On behalf Management of KCG College of Technology and Department of Information Technology, I welcome our speakers, Professor Shekhar Verma, for this afternoon session. Welcome you, sir. Now we can take over the session, sir. Thank you.
Thank you for the nice introduction, ma'am. And I thank the KCG College for inviting me and for considering me as a speaker in this wonderful workshop, FDP. And let me start with an introduction. And so this particular lecture will be a self-contained lecture, which will be talking about blockchain. What are the cryptographic tools used in blockchain? Some attacks on blockchain, though I'll not be talking about a lot of vulnerabilities in blockchain, but a little bit of attacks in blockchain. And then if time permits, and I repeat, if time permits, we'll be seeing how blockchain is being really applied to security in IoT and how vulnerabilities in IoT are being plugged using blockchain. So, but the main concentration of the lecture would be on what are the cryptographic tools which are used in blockchain. But as I said, it will be a self-contained story. So I want all of you to relax back, sit back and enjoy the story. With this short introduction, let's start without assuming anything about blockchain. Let's see what is blockchain, why do we need blockchain, how far the blockchain has gone, why is blockchain becoming very important, what are the real ideas behind blockchain, and then what are the applications of blockchain to other areas as well. And everything shall become clear as soon as we understand the reasons for the creation of blockchain, what problems, underlying problems blockchain solves. So let's start. Obviously, don't be very hopeful. As I said, we'll just touch the tip of the iceberg. I'll just be giving you a story. We'll not be really be going into details of anything, neither blockchain, nor cryptocurrency, nor crypto on blockchain, but it'll be a story. And let's see how the story goes. So let's see, here are two ladies, and if they want to exchange money for anything, then cash payment, a physical cash payment is a norm of the day. So both of them need to be at the same place in physical proximity, exchange cash. So what exchanges is the cash. And the whole idea of blockchain would be then to make the payments anonymous. So let's see if in cash payment, what is the anonymity that we have? So what happens in cash payment is this lady here withdraws cash from the bank. This lady also withdraws cash from the bank. Both of them go to a restaurant or a particular shop, get some service. Now here is the shop owner and he wishes to know who has taken the service. Is this lady in red, or doing some dressed in some Bharatanatyam style, or this lady here below who looks more modern? He tries to find out who has availed the service. And what happens is that in case of cash, remember, when we go and buy something, when we go to the hotel and eat, we need not reveal who we are to eat. or who we are to buy something. And the cash and the physical cash is totally anonymous. So this anonymity is what we want in the digital world. So the basic idea and the single most important problem that we need to solve, or our objective, is to replicate the physical world in the digital world. So that is all we are trying to do. And let's see how can this be possible. So the first attempt, say Paytm, PayPal, Google Pay, and other means of digital asset exchange came into being. And what was happening there, if this girl here in Bharatanatyam dress and this girl here, Gauri, they wish to share money or transfer money to each other, both of them would draw money from the bank. The problem is that this PayPal app is there stored at both the places, at both their mobiles, and the bank, the Paytm or the PayPal app, they both know who is exchanging cash with whom, or who is exchanging digital asset with whom. So, as against physical world, this digital asset exchange breaches the privacy. So this first attempt, or this most prevalent attempt, does not preserve the privacy of the either party. So the question is, can we, again, the same question, can we think in terms of a method in which the exchange does not reveal our privacy? Or can we have anonymous exchange? So is the answer, what is the answer? The answer is yes. And the answer is that we can have an electronic payment system based on cryptographic proof instead of trust. So blockchain solves this problem. And one of the applications, or the foremost application of blockchain, which is the cryptocurrency, solves this problem of digital asset exchange while preserving the privacy of the endpoints. Not just the privacy of the endpoints, but how much cash or how much digital asset or how much money has been transferred. This is also to be kept private from others. So what we want, and what does blockchain do? Blockchain solves the anonymity problem while maintaining all other properties of the digital and the physical cash. So let's have a look. What is our wish? So our wish is that I have a distributed system. Why distributed system? Because I want to be anywhere in this digital world. So I want a distributed system in which the money is distributed, exists in a distributed manner. I don't want to trust even the bank, because the bank breaches my privacy. I don't want a centralized authority like a bank. I don't want to trust a bank, or I don't want a bank. And I still wish to have money while preserving my privacy. I don't want anyone to know who I am, whom I'm transferring money, how much money is being transferred, whom is the sender, who is the recipient of money. So I want total anonymity of the sender, the receiver, and the transaction. But I don't want a bank. How do we solve this unseemingly unsolvable problem? So the first thing is, I want the bank to be eliminated. How do we eliminate the bank? We say that we don't have, what does a bank do? Let's look at what does the bank do. What does a bank do is it maintains a ledger of how much deposit you have made, how much you have taken from the deposit. So it maintains a ledger whose integrity is always maintained. The deposit left is equal to the total deposit minus the debit, or the total deposit is equal to the deposit plus the credit made. So I don't want a bank. So what I want is to replace this centralized ledger with a distributed ledger or database. And what happens is, as soon as you distribute it, I maintain my own ledger. So what I'll do, in case of coins, it's a physical asset. In case of digital, it becomes a digital asset which can be copied. So there is a fundamental problem that I can issue two transactions for the same coin to do different recipients. In case of bank, if you to issue two different checks for the same amount of money, and you have just 10 rupees in your bank, and you try to give those 10 rupees simultaneously to two people, the bank solves this problem by doing it in a sequential manner. I want to solve this problem in a distributed world. I want to maintain the integrity of the database. I want a distributed database. I want people not to cooperate, because then what is going to happen? I'll make transactions only with people whom I know. So I don't want people to cooperate. So what do I want? First thing, I don't want the bank. From a centralized scenario, I wish to move to a distributed scenario and still have all the advantages of the bank. I want to detect and I want to prevent falsehoods. I don't want any cheating. But then we know that to maintain the integrity of the ledger, and everybody has the ledger, everybody must agree that this is the state of the ledger. But everybody would like to cheat. Everybody would like to say, okay, I have more money. I have not spent the money, or will try to do a double spending, thereby somehow disturbing or violating the integrity of the distributed ledger. How do we have a consistent state of the ledger in a distributed environment is the problem of blockchain. So what is the problem of blockchain? There are ledgers being maintained or database being maintained at different places. I want to have a consistent state of the distributed database in an uncooperative environment. And this we know is an NP-hard problem. So I wish to solve the NP-hard problem, which is called the Byzantine generals problem. What is that problem? To reach to a mutual agreement or a consensus in a non-cooperative, trustless environment. And how to solve it? We find that this is an NP-hard problem, yet we wish to solve it. So blockchain, what does it do? Blockchain aims to have a distributed system. So what it does, it says get rid of the central bank. I want to create coins, maintain the integrity of the distributed database in a distributed manner without having a centralized authority for synchronization, for maintaining of the integrity, etc., etc. So what is the key challenge? The key challenge is to have a consistent state which says that there should be a consensus among all participants without a central authority and without trusting each other. I do not trust. I want to cheat everyone. Everybody wants to cheat everybody else by doing double spending, by doing some other thing. But I want, the aim of blockchain is to be able to have a consistent state of the distributed system without a bank, with all participants not trusting or not cooperating with others. So that's the grand aim or grand objective which blockchain tries to solve, and of which Bitcoin is a very, very prominent application. So what does it do to start with? It says everybody is a bank. So everybody maintains the record of everybody else. Is that fine? Everyone is a bank. I repeat, everyone is a bank. Everyone keeps the record of everybody else. So there is no problem except that the size of the database is going to grow like anything. So what we are going to do is we are going to use a cryptographic technique like hashing so that we are able to reduce the size of the ledger. So I want a distributed ledger, which is same copy should be there with everywhere that reflects the transactions and the ownerships. And the blockchain is what is this distributed ledger. So what is this blockchain? Blockchain is the distributed ledger which reflects the transactions and ownerships, and the copy of the blockchain is kept at every participant. And to overcome the problem of the size of the database or the ledger, we do hashing so that the size of the ledger is manageable. And as I said, Bitcoin is one such application. So to do this, do what? Number one, to be able to maintain the integrity of the transaction, to maintain the integrity of the blockchain, to maintain the blockchain, and to have consensus in a trustless, asynchronous, non-cooperative environment, we say, what can we do? So we turn to cryptography. And I also want the privacy of the sender, privacy of the receiver, anonymity of the transaction, the amount of transaction. Hence, we resort to cryptographic techniques to achieve all these things. So for the initiation and broadcasting of transactions, we can use digital signatures, which will also somehow protect my privacy. The validity of transaction or the integrity of the database is, or consensus is reached in a non-cooperative environment by using some proof of work, a proof of stake, a proof of burn, a proof of luck, a proof of authority, a proof of time elapsed, or some other method like in Hyperledger, so that we reach to a consensus so that the blockchain is in a consistent state and there is a mutual agreement between participants of that particular state. How do we maintain the integrity? By chaining blocks. So all transactions are taken, hashed, so that nobody can have another transaction with the same hash function, because there's a pre-image hardness. So we use hash functions. So what is a blockchain? Blockchain is nothing but the chain of blocks which contain hashed value of a group of transactions. How do we maintain the privacy of the and unlinkability of the transaction? By using some ring signature or traceable ring signature or some zero knowledge protocol, which Mr. Shubham will tell you or may have already told you. He'll be talking about zero knowledge protocols in blockchain. How do you protect the members? By using some verifiable random functions. And how do you communicate? By using secure multi-party computation. These last two I'm not going to talk about, but we are going to talk about all other cryptographic techniques which are used for maintaining the integrity of the blockchain, for having privacy of the sender, receiver, the anonymity of the transaction, the integrity of the transaction or the hyperledger or the ledger itself. So if you want to view a blockchain, then it's a distributed database only. So from data management, computer science perspective, it's a distributed database in which, as the transactions are happening, we chain the transactions and maintain a chain of the transactions. From security point of view, we say that there is a network in which there are distributed participants which are distributed and they communicate through a peer-to-peer network. And there is a consensus protocol for mutual agreement between participants regarding the state of the blockchain or the distributed database. And how do we get to this consensus protocol by using some intelligent and decentralized cryptography in which everybody participates. So it's there with cloud computing. So to sum up, blockchain uses cryptographic techniques to ensure the integrity of the ledger. And the integrity, why it is important? Because the integrity of the ledger tells how much has been deposited, how much has been created, how much has been spent. And this is being kept at every place. And this humongous database of transaction is kept to a manageable size using some hashing, which results into blocks, and we chain the blocks. Remember, the most important thing is that you have to reach to a consensus regarding the consistent state of this ledger in a non-cooperative environment, in a trustless non-cooperative environment. So let's talk of the cryptographic techniques. And this is an evening in IIIT Allahabad. So the integrity of the blockchain is used using some cryptographic hash functions. So how do we maintain the integrity of the ledger? By maintaining a Merkle tree. What we do is we take the transactions and put them together. So for a period of time, whatever transactions have happened, we put them together, hash them, and make a Merkle tree. So what we do is we hash one block, we hash a part, we hash another part, we hash them together and then concatenate and again hash them together so as to build a Merkle tree. For example, the Hyperledger version 0.6 has a bucket hash tree, or the Ethereum takes a Patricia Merkle tree or a trie, and a trie is taken so that searching is very fast. So we maintain a tree in which every node is actually a hash. And all the roots, so what is happening? We are hashing and we have a root and we chain these roots. So for every 5 minutes, of every 10 minutes of every group of transaction, we take them, hash them together, prepare a block which points to the previous block. And this creates a chain of blocks. So what is a blockchain? A blockchain is a way to encapsulate transactions in the form of blocks, where blocks are linked through cryptographic hash, and since one points to the previous one, creating a chain of blocks, and this particular tree or chain of blocks is kept with every node. So there is a start. Right from the beginning, there was one block and the whole thing is growing over and over again through the period of time. And there's a pointer in every block which points to the previous block and also contains a hash of the transactions. And since the cryptographic hash cannot have the same hash, because there's a pre-image resistance is there, and hence you cannot have another set of transactions for the same set of hashes, and hence you cannot really violate the integrity. So the integrity of the transactions is maintained using this hash function. So each block consists of its hash, the hash of the previous block, a timestamp, and some other fields. And through this, you create a Merkle root hash, which represents a set of transactions, and these are chained together to form what is known as a blockchain. So this is a figure. We have n plus 2th block, which is a more recent block, which contains a hash of the current transaction, the previous one. There's a timestamp, there are other things which points to the previous block, and which is repeated with the entire history of transaction is maintained in a chain, in a blockchain structure. and this is kept at every place. So this is how it looks like. So what we use for integrity protection is a strong cryptographic hash, which has pre-image resistance, which has collision resistance, and which takes an input of arbitrary size and maps it to fixed size, thereby reducing the total size which needs to be saved. So by just storing a small part, that means a small map, which is the hash of all the transactions in a particular period of time, we make the transactions non-copyable, thereby making them, by preserving the integrity of the transactions, and still store very small size of hash. But then the question is, where else this cryptographic hash function is used in blockchain? We can see it is used at many places. It's used for solving cryptographic puzzles, it's used for address generation, it's used for shortening the size of the public addresses, and it is also used in signatures. But then let's see how they are used. So what is the cryptographic hash function usually used? A hash function is usually SHA-2 is used, which is takes an input of arbitrary size and produces output of fixed size, which is 256 bits. The IOTA, the blockchain proposed for Internet of Things, has its own cryptographic hash function known as curl B, which is not very popular because it's not very strong. So SHA-2 is something which is strongly used and is popular here. So as I told you, that cryptographic hash function is used, and what we do is that this SHA-256, which takes an input of arbitrary value and outputs a constant bit length of 256 bits, is what is used, is known as SHA-256. The D is a hash function which is actually used in blockchain. We said that in a distributed ledger, we maintain a hashed block, and this block is chained, which protects the integrity of the distributed ledger. And this replaces the storage of the actual transactions. But then who runs this particular hash function? Who is actually taking the group of transactions and hashing it and updating the block? Remember, what I said initially was that it's an uncooperative world. It's a trustless world. So anybody who gets this work of hashing and keeping and updating the block may cheat others. So I want someone, or the participants want someone who can do it. It can be verified by others, but we need to designate someone who will do this particular hashing and updation of the blockchain. So let's see who does it. So this process of reaching to a consensus as to who is going to do this is what is known as a consensus mechanism. So in consensus mechanism, we try to formulate a method so that in an uncooperative, trustless world where there can be cheating, where people can make cartels, people can join together. So democracy failed. You cannot really vote someone to do the updation, because then people with malicious intentions will just join hands and then they will maintain or update the blockchain. So I don't want people to make groups or cartels. I don't want a Byzantine attack, basically. So what do? We first look at what is there in the ledger. So the content of the distributed ledger is a blockchain, as recorded by the blockchain, is immutable. That means any and every transaction ever made is recorded forever. I repeat, every transaction ever made right from the beginning of that particular application is recorded for everywhere. And since everything is recorded, and this record is kept at every place, at every participants, they must agree that this is what is the value of the hash. So hash output should be agreed upon by everyone. So we must designate a particular participants to do this hashing, and then can be verified by all to reach to a consensus. And as I said, nodes do not trust each other. And we cannot allow people to group together and launch a Byzantine attack. That means it should be tolerant to Byzantine failures. So different consensus protocols have been proposed, like proof of work, proof of stake, proof of burn, proof of activity, proof of authority, and proof of luck, proof of space. And as I said, we had thought that this particular process of reaching to a consensus is an NP-hard problem. Remember, I said that this is a Byzantine general's problem, which is known to be NP-hard. However, it was found that this is actually NP-hard in a deterministic environment. However, in a randomized environment or in a probabilistic world, we can reach to a consensus. And blockchain methods use a probabilistic consensus mechanism, and hence the consensus mechanism or the protocol can be visualized as a randomized leader election process. So we move from deterministic world where the problem of electing a leader to do the updation of the block is an NP-hard problem, to a world which is random and where we can go in for a leader election process. So what is consensus? So a consensus is a method for replacement for trust. It is easy to prove. It is difficult to fake. It is easy to prove that I am the winner of the election, but somebody who is not a winner of the randomized election process cannot fake this. And the initial, as we will be concentrating on a very important consensus mechanism, which is proof of work, which relies on cryptographic hash. But as you can see, we have different consensus reaching mechanism. For example, we have proof of work with Bitcoin. We have directed acyclic graph for IOTA. We have proof of work and proof of stake for Ethereum. We have bespoke for Sawtooth. We have in permission blockchain like Hyperledger Fabric, we have PBFT. We have for multi-chain, it's round robin, and so on and so forth. So what is a consensus mechanism? What is a consensus mechanism? The method for deciding who is going to update the blockchain. And everybody must agree as to who is going to update the blockchain. So this is a consensus building exercise for who is going to update the blockchain. So again, as I said, we are going to use a hash mechanism for doing it. Why a hash? It is pre-image resistant or it is collision resistant. If you look at the example, we have just changed this particular small f by a capital F, and the output of the SHA-256 changes drastically. So we look at this particular, some hash based cryptographic puzzle is given. So what do? We say, okay, I'll give you a puzzle to solve, and there is no algorithm to solve the puzzle. There's no method, there's no algorithm to solve the puzzle. For example, I'll give you, if you want to factorize a number, remember we were there in class 3rd, 4th, 5th, we were given a number to factorize. So we used to divide by 2, then we used to divide by 3, then we used to divide by 5, then we used to divide by 7, then we used to divide by 11 to do the prime factor, and so on to do the prime number factorization of any number. There was no algorithm. We had to actually do it using some brute force method. The same thing is that if you want to find out the input from the output, that means inverse image, then what is going to happen is in hash, there is no algorithm. So this has to be done with brute force. That means this is proof of work. It will show that you have really put in a lot of effort. So what is the puzzle that we give you, or what is the problem that we give you, is to find a hash with n zeros at the start of the input. So what is the problem? To find a hash with n zeros at the start of the input. So if you are given a number and then we say, okay, you find a hash with n zeros at the start of the input, then we know that you'll have to really do some 2 to the power n computations. For example, if you have the value, this is the value. Now I say that I want a hash which has 1 0 in front. So this will take, so there is a nonce. What is to be added so that there is 1 0 at the start? So this will, you will do a lot of exercise, keep on repeating. So if I say, okay, I want 2 zeros in front, then you'll have to do all the exercise. If I want n zeros in front, then you'll have to do 2 to the power n computations. So what is happening, as you can see, if you don't want any zeros, it will take 3 into 10 to the power minus 5 seconds. But if you just want 8 zeros, it will take some 4,886 seconds, which is more than half an hour. So just saying that, okay, I'll give you a puzzle which will say, okay, to solve this puzzle. And what is the puzzle? That I want a hash with n zeros at the start of the input. So you know the input, but I know I want a hash with n zeros at the start of the input. Then you'll have to really work for 2 to the power n computations. We don't have an algorithm. So if the input is random, is not known to you beforehand, then finding out a hash with n zeros at the beginning and n is also decided then and there, then that becomes a problem. So this, and anybody who wins this game, so this forward calculation of hash is very easy, very fast to verify, but very difficult to do. So this can be used as anybody who wins this game has a right to update the blockchain. And he is given some incentive as well. But then the whole idea is that I want people to work. No, anybody can win. Winning is luck, and winning is a proof of work. Better, more and more computation power I have, I'll win the game. And hence you cannot really 10 people joining together online will not be able to win. And this defeats, and this leads to a randomized leader election. And this is what is known as proof of work. So this process is known as mining. So mining is a process for reaching to a consensus, and mining is through proof of work is a consensus reaching mechanism. Anybody who is able to solve this cryptographic puzzle is given the chance to update, or the right to update the block. So what is mining? Mining is a process of creating a new block, and who gets a right to mine the block is one who solves the cryptographic puzzle, and he's called a miner. So I am given the version, I am given the hash of the previous block, I am given the current transaction. We have to do what? We have to make a concatenation and add some random number, and this is what we said, and add some non-random number, and such that this particular random number, or n ones or nonce as it is known, you need to add so that the hash value becomes less than a particular threshold. So this threshold is what is given, This version is given then and there. The hash of the previous block is known, but the current transactions are known only at that time. I wish to find out an end once so that the hash has a number of leading zeros. We have to have nonce such that the output has a leading 8 zeros. So this takes time, and this is proof of work. And this is what is shown in SHA 256D. You have to do this multiple number of times so that you are able to solve this problem. And there's no algorithm for doing it. And hence we say that this is hard. How hard it is equal to the number of leading zeros that I want. So again, what I want to say is that this involves a cryptographic tool, which is a cryptographic hash function. Mostly SHA 256 is used 2 times, which results into SHA 256D. So what is a hash cache protocol? The hash cache protocol works like this. Suppose an email client wants to send an email to an email server. The client and server both agree on a cryptographic hash function H, which maps to a length n string. The email sends a challenge C. The problem of the client is to find out a string X such that the hash starts with K zeros. And this is what is the proof of work problem. What is the problem? I repeat, the email server sends a challenge string C. What does the client do? It has to find a string such that the hash of the concatenation of these challenge string and the nonce or the string has K zeros. So that means its value should be less than a particular threshold. And for this, it has to work hard, and it has to work depending on the total number of zeros, leading zeros the hash value should have. And this is what is known as proof of work. So whosoever wins this proof of work updates the blockchain. So the basic mechanism of blockchain is now clear. I maintain a distributed ledger at every place, number 1. Number 2, I am able to defeat the non-cooperative, trustless nature of everyone by using a mining algorithm, which is also based on cryptographic tool, which is a cryptographic hash function, and the protocol is called hash cache protocol. Now let's see, everybody is distributed over the network. So what is an attack? What does an attack constitute of? So the attack is mainly on the network infrastructure. The first attack is based on the observation that blockchain is maintained by a peer-to-peer network, which works on top of the internet. And if I am the winner of the hash cache protocol, I am winner of the proof of work, then I need to update the block and send this view to everyone so that the other transactions may now be counted for the next round of POW. So I can attack this so that there is a non-consistent global view of the blockchain. Why? If there's a propagation delay or a synchronization problem, then nobody is going to know who is going to do this proof of work, for what set of transaction. So synchronization is necessary, and if I can attack the synchronization, I can attack the blockchain. So the first attack, which is known as net split or the eclipse attack, is the adversary monopolizes all the connections. So it says, okay, all routes through the other node passes through me. I am the neighbor, and then splits a particular node from the entire network. So that those nodes who have been isolated from the network cannot participate in consensus. And this may cause inconsistency in the network. Similarly, If there is a routing and I am a part of the routing path, then I can unduly delay the message passing. Or if I am an articulation node, I can just isolate a set of participants. I can create an isolated island so that the total block propagation is delayed in the network, thereby disrupting the blockchain. Similarly, I can launch a distributed denial of service attack. So here, especially what I can do is the adversary exhausts the network resources and targets honest nodes so that they don't get services, and hence they cannot participate in the blockchain or the updation process. So these are few attacks which can happen. But then let's move to some other important problems. And there are solutions to the attacks, but let's now move on to other problems or other objectives which we want a blockchain to have. So let's see what are the problems that we wish to have. And the other objectives that we need to go in for is untraceability and unlinkability. If I do a transaction, I don't want to be traceable. If I am the receiver, I don't want to be linked to any transaction. And both the parties, the sender and the receiver, do not want the amount of transaction to be revealed. So privacy and anonymity, privacy of both the parties involved in a transaction and the transaction itself demands anonymity. And how do we achieve it? Let's see. So let's look at one example. The initial Bitcoin network, the amount of transaction was not private. And the hiding behind the public key or using pseudonyms was not sufficient, and sender and receivers were not really private. Why? Because the blockchain checks how much amount you have to verify, and hence every fund could be checked, thereby revealing or breaching the privacy of the sender and the receiver, and the amount of transaction was also in the public domain. But what do we want? We want untraceability of the sender. That means for all incoming transactions, we wanted to say, okay, we cannot really pinpoint to a sender, and every sender is equally probable. Similarly, I don't want to link a transaction with the receiver. So this is how it looks like. Linkability says you can link two transactions to a particular receiver. So transaction 1 here and transaction 2 here can be linked to this particular receiver. Unlinkability says that you cannot say who the transaction is coming from. And remember, this was there in the physical cache. While taking the cache, you cannot say who it comes from. Untraceability says, I don't want who is the sender. So I don't want traceability of the sender. This is also true in physical money. And we want to replicate this privacy in the digital world. Not only that, I want one more thing. I do not want to reveal how much is being transacted from third parties, except the sender and the receiver. But remember, having said this, that I want to hide the sender, I want to hide the receiver, I want to hide the amount of transaction, but I still want verifiability of the transaction. I don't want to disturb the integrity of the blockchain. So verifiability has to be there, but at the same time, paradoxically, the amount of transaction should not be revealed. So for this, in blockchain, in Bitcoin, there was one plugin which is known as Monero. What does Monero do is, Monero generates public key and private key using elliptic curve cryptography. And for untraceability, that means we don't want to know who is the sender, but to still verify that it is coming from a legitimate sender, we use ring signatures. And ring signature, what does it do? It takes the private signature. A person who is going to make a transaction takes his own private key and takes the public key of his neighbors. Who are the neighbors in this case? The persons who have just made some transactions. So we take the public key of the other parties, some parties, and I take my private key, sign the transaction. So the transaction is legitimate, verified. However, I cannot be pointed. So there'll be one of the persons in that ring who is there, it's not known. And then we use stealth addresses to may have unlinkability with the receiver. And we shall see what is stealth address as we go by. So what do? For verification, I use ring signatures. The blockchain uses ring signature or uses a digital signature, ring signature based on some digital signature. So what is a digital signature? It's based on public key cryptography to produce short keys called signatures. So usually what is done, we take the message which needs to be signed, we hash it, and then sign this or encrypt this particular value of hash. So how do we really produce a particular signature is by taking the message, hashing it, and then encrypting it. Or we can encrypt and hash or hash and encrypt. So what we do is every transaction needs to be signed, which authenticates the sender. And if you are going to use ring signature, you are authenticating the intended sender without actually revealing his ID. And a signature, as in real world, also provides integrity as well as non-repudiation. What is non-repudiation? If you see a document, for example, if you sign it using your physical signature, tomorrow you cannot say that I have not seen it. So this is a non-repudiation property. So a signature is doing a lot of things. Number one, it is authenticating the sender, because not everybody can create somebody else's signature. So nobody can create anybody else's signature. So if there is a signature, that means the authenticated party has signed. Since the transaction can be made only by a person, legitimate person, hence transaction integrity is also ensured. And finally, a signature also says that the party who has signed tomorrow cannot say that I have not signed or I have not seen, and hence non-repudiation is also achieved. So the signature scheme is used for privacy of the transaction, privacy of the sender, and so on. And unlinkability also, because you cannot link a particular transaction and the sender actually hides behind the signature of the public. So this is how transaction takes place in a blockchain. So what do? We have a transaction block, we create the hash of it, and then with the signer's private key, you encrypt it or sign it, and creating the output of a digital signature, and this is there in the transaction block. Similarly, like verification of any other signature, this can be verified using the public key of the signer. So the signing requires the private key of the signer, the verification requires the public key of the signer, and this is how you verify the signer and authenticate the signer. And obviously the transaction integrity and non-repudiation is also achieved. So let's look at what are the signature schemes which are used in blockchain. So number one, multi-signatures. So what is used? What important here is that not one person's signature is sufficient. I want a group of participants to sign. So if the group of participants do not sign, for example, in blockchain platforms like open chain and multi-chain, then it's like a threshold signature. Suppose there is a meeting and we want at least M people to come and attend the meeting. So there'll be a valid meeting only when M out of N people come and put their signatures. So this decreases the risk of theft. There's a blind signature in which the signer does not know the content of what is being signed. He puts in a blind signature. That means if he sees a hash and signs on the hash, he does not know what is the original transaction, but signing on the hash, he can do because of the pre-image resistance. So a blind signature is used in blind coin to achieve unlinkability of the transaction. So a blind coin uses a blind signature. And what is a blind signature? The person who's signing does not know the actual amount and yet signs. Then, as I said, similar to multi-signature, we have a threshold signature in which a threshold T out of N parties must be there to create a signature. And this provides an anonymity because we do not know who is you cannot really reveal who is the one signature is being put. We have to know because there's a group, there's a threshold, the anonymity of the individual is maintained. And then this is a signature, is a ring signature, which is actually used. And I told you in Monero, what do we do is the signer takes its own private key, takes the public key of the users who have just made a transaction because the public key is available, and creates a ring signature using this group. Ring signature has a property that the signature is valid, proves that one of the people, one of the parties who is there in the ring of public keys has signed, but it does not know who has used his private key to create the signature, and hence it allows you to make untraceable payments. And thus the sender privacy is maintained, or ring signature gives you an unconditional perfect anonymity for the sender. So in Algorand and other methods, we, instead of using a ring signature, what we use is a zero knowledge proof. I think Dr. Shubham will be speaking on this zero knowledge proof, so I'll not be going into details, but then I'll just touch upon how zero knowledge proofs are used for making untraceable and unlinkable transactions. So what is a zero knowledge proof? To start with, so what do we do in a zero knowledge proof is we have a prover, we have a verifier, and a prover is able to prove to a verifier some statement and proves the validity of the statement to the verifier without revealing any other information except the statement. Okay, what do you mean by this? The thing is, I say that I have a yellow ball. Without showing you the yellow football that I have, if I am somehow able to prove that I have a yellow football, then this is a zero knowledge proof. So what does zero knowledge do? In this, the prover asserts some statement to be true and proves its validity to the verifier without revealing any other information except the statement. Here, in this case of blockchain, we prove the statement that the transfer of an asset is valid. That means a transfer of an asset is made without revealing anything about the asset. So we do not know who has made a transfer to whom and what is the quantity of that particular transfer or that particular asset. So this provides confidentiality of the asset in the blockchain while keeping the asset in the blockchain private. Who uses that? Zero coin and zero cash protocols. They have been proposed for untraceable and unlinkable transactions using zero knowledge proofs, or zero knowledge proofs. So how do we do? How does zero coin achieve this? So zero coin can spend, any user can spend or his her Bitcoin by producing a secure commitment, recording it in the blockchain, and broadcasting a transaction with a zero knowledge proof that I am the owner of the Bitcoin or the zero coin, and then transfer that particular zero coin. As I said, I will not go into details, but I'll tell you what is the protocol which is being used in zero knowledge proofs. So, as we proceed, what we are saying is that we are going to make a zero knowledge proof. So, what is used is a zero knowledge succinct or ZSK SNARK protocol is used, which is zero knowledge succinct non-interactive argument of knowledge. And what is the idea? Is that any computation condition can be represented by an arithmetic circuit which takes some data and gives an output as true or false. I'll just try to explain this long sentence. So for example, I wish to prove that I know my way through a particular tunnel. So I go through some path and emerge out of the tunnel at the other side. Nobody finds out what is the way I have gone through the tunnel in. So if nobody sees that, okay, people say, okay, but you may have gone some other way. Why don't you use this particular way to go in, or use that particular way to go in? So probabilistically, sometimes I'm able to make an entry and come out. Probabilistically, sometimes I'm not able to come out. But then if I am able to come out sometimes, then probabilistically people might say that, yes, he knows a way out of the tunnel, which is, but nobody knows what is the way out of the tunnel, and this is a zero knowledge proof. So this zero knowledge snark is what is used by Zcash, a zero coin, in achieving privacy and anonymity, and it's used by zero cash or quorum blockchain for transaction privacy and anonymity. As I said, that I'm not going to details because Dr. Shubham will be dealing with, or may have already told you about the zero knowledge proofs in Bitcoin or blockchain. What is used in zero knowledge, but I'll tell you this, is that we use zero knowledge succinct non-interactive argument of knowledge, which is a non-interactive zero knowledge proof with no interaction between the prover and the verifier. That means there are not multiple rounds of interaction, but there's just, I produce a statement and the other person believes my statement without any interaction. And he believes that what I've said is right without telling me or without seeing what is right. So a zero knowledge ZK SNARK protocol uses a common string, reference string, and this is used for computational zero knowledge without requiring any interaction. So what is zero knowledge? The client or the verifier learns nothing about the validity of the computation. It's succinct because the proof is very short, does not take any time. It's non-interactive because there is no exchange. It's just there's no interaction. And this is what is ZK SNARK protocol, which is used by Zero Cash or Zcash. So some more details. So we have a common reference string. Both parties have access to a common string, which is some random data. And this is created in a trusted way through secure multi-party computation. And the main idea is that you have a computation, and this computation Px into Qx is equal to Sx into Rx can be done very easily. And we do this in encrypted domain. And the idea is that we are able to prove this in encrypted domain by using homomorphic encryption. So So what do is we don't supply px0 or qx0 or sx0 and rx0. We apply or give only the encryptions of these values, and we know that in using homomorphic encryption, the multiplication in the encrypted domain is equal to the encryption in the unencrypted domain, and hence we can verify this without knowing the values of px0 and qx0, and hence we can verify anything. I know I have not given you any idea of how zero knowledge protocol works, but this is long, my friends. I think Dr. Shubham will deal with it. So what are the other cryptographic techniques which are used in blockchain? For encryption, we usually use symmetric key encryption. So if you want to encrypt some smart contract, we use symmetric key. Usually an AES is used. For example, symmetric key encryption is used in Hyperledger and in blockchain. In Monero, we use homomorphic encryption for range proof, or as we have seen, and even in zero knowledge proofs, we have seen homomorphic encryption being used. Now, finally, we talk about commitment. And what I'll do is, I'll be talking about commitment. What kind of commitment scheme does blockchain use? And what is the cryptographic method used for commitments? So, the commitment used is what is known as Peterson commitment. And again, as I said, I'm talking not without a lot of context here, but then let's see what is a commitment scheme. So it's a two-phase game. I'll give you an example here. Me and my friend, we are in this COVID time are there in two different places, one at this part of the city and another at another part of the city. We wish to go for a party. And what we say is, let's decide. I say, if you toss a coin, I toss a coin. If we both of us get heads, then I will pay. If both of us get tails, then I'll pay. If there is a head and a tail or a head, then you pay. So me and my friend, I repeat, toss a coin at individual ends. I toss a coin in my room. He tosses a coin in his own room. If I get a head and he gets a head, or I get a tail and he also gets a tail. So if we have the same value of head or tail, then I give the party. I pay. If I get a head and he gets a tail, or he gets a head and I get a tail, if the tosses are different, then he pays. Now he is cheating. If I say I've got head, he says I've also got a head. If I say I've got a tail, he says I have also got a tail. So that only I pay. How do you overcome this particular problem is what is a commitment scheme. So what we do, I generate a random number. So what I do is I generate a head. So I toss a coin, I get a head. I generate a random number, concatenate that at the end, hash it and send that hash. Now he does not know what have I got a head or a tail. What he has got is just a hash. And what I do is I also send the random number. So what I've sent, I sent the random number, I sent the hash value. But he does not know where I have kept my head value, whether I have concatenated the front, back, middle, or wherever I wish to. So he gets a tail and said, I've got a tail. Now he said, you reveal what you have got. So what I do is I just tell him that this is the position of the head that I have got. Put it, hash it, and you will get the hash value. I cannot cheat because I have made a commitment. I cannot do a pre-image. So my commitment I cannot change. He cannot cheat because whatever he gets, he says, because he does not know what I have got. So this is a commitment scheme. So in transactions also, a transaction is committed and you cannot change your commitment later on. And hence, if you have committed 100 rupees, you cannot say, no, 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 okay, I'm not committing just 50 rupees. So a commitment is as good as paying. So what is a commitment which is used? The commitment which is used in cryptography or in blockchain, the cryptographic commitment scheme is what is known as Peterson scheme. And let's see how this works. So it's a two-phase game. There are two parties. In the commit phase, it has both hiding and binding of a secret. That means I take a random number and bind that particular random number, bind my secret to the random number, hash it and send it. And the second party, what it does whatever it wishes to, and then say, if you want to reveal what is the secret, I reveal my secret. And then he hashes and says, okay, the commitment for you have made is correct, and hence whatever value you are saying now is also correct. So the commitment scheme has two properties of hiding and binding. The hiding part ensures that the receiver cannot see the message before the open phase. The binding ensures that the sender cannot change the image after the commit phase. So by using a random number and hashing, by binding the secret with the hashing, changes everything. And this is what is done in Monero to hide the amount of transaction. So for verification, we give only the commitment part. We don't give what is the amount of transaction. So by committing, we commit a value and mask that value by not, and I don't need to really reveal the amount of transaction for verification of the transaction. And this is what is used for hiding the amount of money, but still verifying that a valid transaction has been made. So let's see what is Peterson commitment. So it uses, for example, I want to bind a serial number S to a 0 coin Z. So a commitment is made using discrete log where C is equal to G to the power S, H to the power Z. Mind you, if you do not know what is S, not given S, given C, given G, given H, you cannot calculate S. So, and even given, so the user chooses S and Z, computes C. S and Z cannot be computed from C, even if we are provided Z or provided S. So as a consequence, what happens when the serial number S is published, the users can say, okay, I created C by showing Z. So what do? We are saying that when this is published at a later stage, then I can say this belongs to me by revealing S. Nobody can create a C without knowing S or Z, even if you know C, G, and H. So this is a commitment scheme for hiding the value of transaction in blockchain. Now, friends, let's see what we can really do with this blockchain. This blockchain is it's not just for Bitcoin, it's not just for cryptocurrency. It can be used for many applications. And what kind of applications? Wherever we want to maintain the integrity of the system in a distributed manner. So wherever we want to have integrity, we can use blockchain. Why? Because it's a distributed ledger where its integrity is protected through some consensus mechanism. Where we want privacy of the sender, privacy of the receiver, we can use blockchain. Wherever we want the integrity of the data, we can use blockchain. Wherever we want to hide the amount of data which is flowing, we can use blockchain. So for any application, right from supply chain management to IoT to business, we can use blockchain. And let's see an example of how we can use blockchain in Internet of Things environment. So let's see. And let's see first a little bit about blockchain for those who are not really aware of blockchain, little bit of history of blockchain. We still have half an hour to go. So probably I can take the liberty of taking you through a detour of IoT, and then we'll see how do we really apply blockchain for securing IoT applications. So let's have a look. So first thing, what IoT signifies. So IoT, my friends, is a fourth industrial revolution. The first one being the steam, which changed the human civilization because we had a means of energy. The second was electricity, which is still changing the world. We know without electricity, we go into the old Stone Age. Everything is powered by electricity. The computers came and they revolutionized the way we are in this world, the way we interact with each other, the way we do our business, the way we do our entertainment. So computers and internet changed everything. And then what has come? What has come? An Internet of Things, in which sensors talk to each other, machines talk to each other, and they monitor the environment, they monitor the human being, and they talk to each other for our better future and a better state of living. Who would have thought of it a few years back? If you say that your fridge was connected to the internet and will be ordering your groceries or ordering your vegetables, or say that, okay, you are diabetic today and you will not be given some sweets to be eaten, then that would have been a fairy tale story. Who would say that, okay, this is also possible? But now it is everywhere. Everywhere and everywhere, it is all pervasive in our lives. Remember, for example, if you look at your own mobile, it has more than 10 to 15 sensors. If you right from accelerometer to GPS to face sensor to cameras to audio sensor, touch sensors, so many things. Then, if you look at your car, it has more than 100 to 200 sensors. So everywhere there are going to be sensors. And it is expected that in another year or so, 2 years, there will be 60 trillion sensors. It says 10,000 sensors per person. And what is it? An IoT is a cyber physical ecosystem. So these sensors is actually connected to each other. They talk to each other, sense the environment, and by monitoring the environment, they send whatever has been sensed and then use this for some decision making using some machine learning process. But then it's a network and we have sensors which are small devices, and what they do is do data transfers. So data needs to be protected. If you don't protect data, then there'll be a threat to the data. My privacy is going to be breached. My data is going to be changed. I want the protection of my data, which is being transacted. I want data protection in transaction. I want data protection in storage. I want the privacy of the sender or the privacy of someone who is being sensed. I want the privacy of the receiver. Does it not seem to be like a blockchain environment? It is, where we have a sender. We want to protect the privacy of the sender. We want to protect the privacy of the receiver. We want to protect the asset which is being transferred, which is data. So if this can be done by using blockchain, then we will probably be able to counter this threat and protect our data and the privacy of the sensed persons and the receiving authorities. But is this a fairy tale? No. Some years back, in the Mirai botnet hack, around 1.5 lakh cameras were hacked and changed into a botnet which blocked internet. There's a NetPetya attack, remember, and a Stuxnet attack, which are actually ransomware attacks, which cripple the plants, cripple port operations, cripple manufacturing, and they want money. So the threat is real. The data threat is real. People are attacking our Aadhaar servers every time there is an attack. Every moment there is an attack to get our Aadhaar data. The question is, why is this there? Number one, it's a distributed system. The sensors are machines. They may not be trusting each other because there's a lack of standardized exchange protocols. There are devices which are coming from different manufacturers. So this is a trustless environment in which there is no cooperation. And we want to protect the data in transit. We want to protect the privacy of the sender or the person being sensed or the environment being sensed and the receiver. So this is a tailor-made situation for blockchain. So no other technique can really do all these things, but blockchain is specially customized and tailored for such situations only. So where is the solution? Blockchain is a solution. Let's look at the blockchain. But before that, let's look at the IoT ecosystem. We have sensors at the bottom. They sense data, forward the data to the gateways or edge computing or fog computing environment, or the data can go to the cloud. And everything is a peer-to-peer network, or everything is connected through the internet. So there's a connection, P2P connection built on top of the internet. So how can blockchain be there? So blockchain can be there where the endpoints or the gateway devices, here the gateway devices are sharing a blockchain. And the data is being passed by the IoT devices, but IoT devices do not maintain the blockchain. The blockchain is there between these gateways. Or the edge devices can just be transaction issuers for these particular data, washing machine, refrigerator, camera, TV. They can be a part of the blockchain, but they will not keep the blockchain, but they'll be a part of the blockchain. They can verify their transactions, but will not update the blockchain. Or they may also be a part of the blockchain. They can be participating full blown in the blockchain itself. So, and if you involve not just the gateways, but also the cloud, then the entire Internet of Things is actually, everybody is maintaining the blockchain. It's quite possible that they may be maintaining private blockchains, and cloud and the edge devices may maintain a public blockchain, but everybody is connected through a blockchain, and it can be a hybrid blockchain because devices may contain only a part of the blockchain, their own private blockchain. Edge devices may share a blockchain with the IoT devices, and the cloud may maintain a public blockchain. So what are the security issues in IoT? Number one, what is the main function of IoT? It senses data, generates a lot of data, passes that particular data. So I want, and the IoT wants, the data should be stored and transmitted in a confidential manner. I want data confidentiality and integrity. What happens in cloud? It's a traditional centralized storage. So you can have a lot of encrypted data put there. But I don't want a cloud type of environment. Why? Because a single point of failure. Everybody wants to store there. If it fails, everything fails. All communication routes are to the blockchain, to the cloud only. So it's a single point of failure, and there's a congestion in the network. The cloud is far off from the Internet of Things or from the actual devices. So there's a delay, there's a problem of scalability. So I want a centralized Instead of a centralized storage, I want a distributed storage. So what is the answer? The answer is blockchain. And I want my devices. So every manufacturing industry has sensors placed at the manufacturing plant, at the supply chain part, in the warehouse part, while you are transmitting the data or sending your goods on the trucks, you have sensors. So sensors are everywhere. And the data is being transmitted from the sensors. So if I say, okay, the trucks are getting delayed, then I'll just modify my supply chain. If there's an undue delay or a problem in the manufacturing plant, I want to change that. But if the data is somehow compromised, then I have a problem. So 35% of the manufacturers nowadays rely on this data by smart sensors to improve their operating processes. But it is quite possible that the truck owners who transmit your goods are different from you. The manufacturers are different. Manufacturer of your parts are different. The truck system or the transportation system owners are different. The persons who are keeping it in inventory are different. So they will not give you data, or they will give you data at a cost. So you want a convenient and fair data trading system. Me as a manufacturer wants data from the warehouse, wants data from the supply chain, wants data from the transporters. I want data from the retailers, but this data is not for free. I have to buy this data. And the data has to be bought, then nobody should cheat anybody else. I should not say, okay, I have got data and I don't pay for it. Or I pay for it and don't get data. It's like just like money. It's just like an e-commerce environment. So I want to enforce fairness in the data trading mechanism without trusting anyone. So it's a trustless, non-cooperative world in which I want fair exchange of data, or I want exchange of assets. And this can be done using blockchain environment. Similarly, I want authentication, I want access control. And this I don't want in a centralized manner, I want in a distributed system. Again, I don't want my data to be there with everyone. Let's look at this example. It is found that smart toy makers like Barbie and this Cognitoys Dino, what they do is they install small sensors in the toys and record whatever is happening and whosoever is using it. And they use this data to make toys smarter. But this breaches the privacy. This breaches my privacy. And privacy preservation, including data preservation and entity privacy, is very, very important. So what is the solution? As we had already said, I want transaction to be done in a fair manner. I want everybody to pay for the data or get paid for the data. It's not that I pay for the data, don't get the data, or I don't get the data after paying for it. So blockchain is able to work in this trustless environment. How does it work? Let's see. So let's see how data trading can be done with confidentiality and while maintaining the integrity of data. So I want data sharing and trading in a transparent and accountable way. I'll give you an example. The example is that I'm a doctor, I'm a cardiologist. I'm keeping a lot of ECG data. And an ECG manufacturer says, if you give me data, I will be able to make better ECG machines. I say, okay, I can give you ECG sensor data, but I want money. But he does not trust me. I don't trust him. So we use a blockchain to effect fair data sharing. And how do I do it? I use a blockchain. So what do I do? Let's look at the figure. He is a buyer he commits some some bitcoins, some cryptocurrency, some D bitcoins he commits using the commitment scheme which I told you, the Peterson commitment. He commits some money. Then the value of the bitcoin he commits is D. So what he does, the data owner collects the data from the IoT system, shares the data at some price. Now, a buyer makes a commitment. So the buyer here, what it does, it says, okay, what I'm doing is I'm committing D bitcoins. Now, what happens is when he has committed data, then this fellow, the other part, the seller says, okay, I have verified that you have committed D bitcoins. So a commitment has been done using this script. Smart contract has been executed. And when he does this, so it's a timed commitment. So the commitment has been made only for time T. So if the seller can redeem the deposit and honestly pays to the seller within time T, there is a transaction made. If the seller does not send the data within T time, then the deposit is sent back. If he is able to sell the data and give the data within time T, then the deposit can be forwarded to the seller after time T. So there are three things. Number one, there is a commitment from the buyer, a timed commitment from the buyer. Then it is verified that a commitment has been made. Then the seller transfers the data within time T. If it does not, then the money is given back. The commitment is given back by the blockchain to the buyer. Else, the deposit is forwarded to the seller after time T with her transaction. So there is a transaction fuse which says that the money has been transferred. So what is happening? The blockchain is working here. I make a commitment, then you send me the data, and if you give me the data within time T, then I will show the number so that the fuse operation transaction can transfer you the money. Otherwise, what is going to happen? The transaction is not made by the seller, then the whole transaction is nullified. So I'll repeat, I'll just say what happens here is in this transaction, a timed commitment is employed. The seller can redeem the deposit after she honestly pays to the seller within time T. Otherwise, the deposit is forwarded to the seller and with the transaction fuse. And if a seller signs fuse transaction before time T, then the whole thing is valid because it has not sent the data. And this ensures that a malicious buyer cannot harm the seller. That it means it has to give the data, and the buyer also needs protection because the seller also needs to generate a transaction to make some deposit. So what is happening, that both parties are making a commitment in the blockchain so that the exchange is fair, and this can work in a non-cooperative trustless environment. Similarly, we can do authentication and access control in IoT using blockchain. So blockchain can provide authentication and access control to smart devices, services, and data in blockchain and removes the dependence on central parties. So here again, what we do is we have a smart contract which has different kinds of transactions, T policy, T access, and T query. So the T policy, we have predefined access policies defined in the smart contract. T access is for access management, T query is for access query. And when a new entity enrolls in an IoT system, it generates a new public key with an access permission, puts a transaction in the blockchain for accessing, which is for access management. When the entity needs to get access to the IoT system, what it does, it generates a query and signs a transaction, which is verified using a public key. And if the transaction is valid, if the query is valid, the authorization is made. So again, we are ensuring the authentication of the new user and previously unknown user using blockchain. Similarly, my friends, we can do device management. See, we have a very small IP address. So instead of IP address, we can use the IP address is just 132-bit or 128-bit. So what people said, okay, why don't we use the public key itself for transaction? So public key, which is 160-bit, for example, in Ethereum, can be used as an IP address or an address. And this hides the device and also gives it a big address. So this is also can be used for data management. So what we are doing is we are using the Ethereum address or the Ethereum public key for identifying the objects using their public keys. But since the device ID is hidden behind the public key, it is also preserving its privacy by acting as a pseudonym. So we can use the public key itself, which is 160-bit here, as an address instead of using 32-bit or 128-bit address, which reveals the privacy of the device. So finally, what people have done is, as I've told you, in a hybrid blockchain, you have a blockchain, internal blockchain, we have an external blockchain. So the cloud has a blockchain with other suppliers and users for supplying and data sharing. Within the company, you have your own blockchain to remain private from other blockchains and have your small blockchain internal to the company. So it's something like this. So we have a lot of private blockchains and we have public blockchains, which are there in the public domain, which you share with your supplier, the manufacturer, the retailer, the wholesaler, and within your own company, you have small private blockchains, and these can interact with each other at appropriate points, but then the privacy is maintained, the integrity of the blockchains are maintained, you are able to make fair transactions, you are able to exchange data in a privacy preserving mode without disturbing the authenticating, and you give access control only to authorized people by having a mixture, a hybrid of private and public blockchains. There can be other applications, but I don't want to go into the other applications because time is running out. But then we can use blockchain for anonymity by hiding behind the public key, and several cryptographic methods have been used. For example, we have linkable ring signatures in Monero, wherein you can hide behind the ring signature. Likewise, you can do all transactions using homomorphic encryption, where you can verify without knowing the amount of currency, because the currency is actually hidden. So in any billing that you do nowadays over the internet, you can do using homomorphic commitments. Or you can verify that a person has done the transaction using some zero knowledge proof. And this particular application can then be privacy preserving. So my friends, what we can do is we can use blockchains at many places, anywhere where you want the privacy of the sender, privacy of the receiver, the anonymity of the transaction or the digital asset, as well as work in a non-cooperative distributed environment, you can apply blockchains. So this is all about the blockchain and its applications. Now for some shameless advertisement. We at IIIT work in security, blockchain, lattice-based cryptography, and IoT. We also work on machine learning. We work in manifold learning. We work on learning on graphs. We also work on privacy preserving learning. We work on transfer learning. The research group is Professor Manish Kumar, Professor KP Singh, Dr. S. Venkateshan, whom you are probably going to hear soon, and myself, Professor Shekhar Verma. We invite you, come work with us, study with us to create a better tomorrow. Thank you. I think I request the organizers.
Yes, sir. Yeah, thanks for your
to
wonderful session, sir. Participants, if you have any queries, you can please unmute yourself and ask.
So I'm open to questions, please.
I hope the participants have well understood the concepts, sir. I really enjoy your session with your real-time examples. So thank you for your wonderful.